So I'm going to talk about the origin and processing of the key material in lithium-ion batteries that we discovered, which was lithium. Lithium is found in more than 150 minerals found within clays, continental brines, geothermal waters, and seawaters. Geographically speaking, the largest supplier of lithium is Australia at 44%, Chile at 34%, and Argentina at 13%. And the graph on the right shows where other key materials are found. The two different conversions of the raw material are through lithium brine, which is drilled from underground deposits, where then the water contents are evaporated, and that mixture is pumped to lithium recovery facility, where it is filtered of contaminants, and solvents and reagents are added to isolate the lithium. Then it is finally treated and filtered. Lithium ore, through its hard rock state, is mostly common in spodumene, where that process is extracted, is heated and pulverized, and then reactants are added, and it is filtered and evaporated into lithium carbonate. So why lithium is used in batteries? Because lithium is a highly reactive metal with a single valence electron. Lithium is present in the cathode of the battery, the positive side, and when the battery is charged, the electrons from the lithium oxide are drawn to the anode. This causes the lithium to be unstable, and it moves across the porous separator into the anode, and it's trapped in this graphite lattice. When the battery is in use, then the electrons are transferred over to the cathode, and the lithium follows over there too. So the properties of lithium in batteries, one of the most common metal oxides used in batteries is lithium cobalt oxide. Its pros are that it's high in specific capacity, has a high volumetric capacity, has a low self-discharge and a high discharge voltage, as well as good cycling performance. Some of the cons are that it has high production cost and has a low thermal stability, as well as a fast capacity fade. Some modifications that are being made to lithium oxide is that through the heat treating of it, which reduces the interfacial resistance between electrode and electrolytes, which leads to better cycling performance for a battery. So when observing the improvements made of the material of lithium oxides over time, the properties we observe are specific capacity, volumetric capacity, and average voltage, which you will see in the next slide. And two examples, one being lithium cobalt oxide, which we talked before. It was the first ever lithium oxide produced in batteries. And the problem with it is that it's high in cost and has low thermal stability. But then there's also lithium nickel cobalt aluminum oxide, which is quite a mouthful, but it has a longer storage life and a higher usable discharge capacity. So that's why it is used by Tesla in their lithium-ion batteries. So here are some other lithium oxides that are used in batteries and their properties.
All right. Hello, I'm Todd Cummings, presenting with Megan Freed and Ben Peacock on lithium-ion batteries. Today we'll be talking about the product itself and its impact on society. We will be talking about the origin and processing of key materials. We'll also be talking about the sustainability and environmental impact of those key materials as well, just to give a great overview of this product. So first, I will be talking about the product itself and its impact on society. So first, why is this of interest to us? Why do we want to learn more about the lithium-ion battery? And that's for two reasons. One, its ubiquitous uses, and two, its environmental implications. So first, the ubiquitous uses. Chances are, if you use any electrical device, you have used something powered by a lithium-ion battery. They're used in smartphones, electric vehicles, laptops, and many more. So the ubiquitous use of it and how commonplace they are makes them very interesting to learn about in everyday material. Two is those environmental implications. They both have benefits of reducing emissions, but some challenges in resource allocation and recycling. So that kind of contrast is a very interesting thing to learn about. So going on the most important materials that make up the lithium-ion battery. First, you have your cathode material, which is anything from lithium cobalt oxide, lithium manganese oxide, or really anything like that of lithium salt. And it's used to construct the cathode in the lithium ion battery, and it plays a major role in determining the battery voltage and capacity. And right here, you can see the different crystalline structures of the anode and cathode materials. Second, you have graphite, which has been dominantly the anode material in lithium ion batteries for the past 25 years and more. Second is this lithium hexafluorophosphate plus an organic solvent of some sort. That is the electrolyte substance that allows lithium ions to flow between anode and cathode, and the choice of that also affects performance and safety. And then we move on to polyethylene and polypropylene. It's a synthetic resin that's used to act as a separator in lithium ion batteries, which is just a physical barrier that separates the anode and the cathode. Now, kind of zooming in on one of the more interesting materials in this product is the cathode material and the selection of the cathode material and how that directly determines capacity and voltage. So if we want to take a look at all of these different cathode materials, you can see that each one has different midpoint voltages, different specific capacities, different advantages, disadvantages, and my face is in there, but different applications as well. So the selection of that really just plays a huge role in determining performance and the determining the performance of the lithium ion battery. So now we go through some important breakthroughs of the lithium ion battery, and it starts with the Hagen-Muller group. In 1973, they conducted many studies using sodium cobalt oxide as the cathode, and that inspired Goodenough et al. In their next study. And what they did is really what changes everything. They replaced sodium with lithium using lithium cobalt oxide as the new cathode. And what they found is that lithium cobalt oxide is more stable in air than sodium, and it has better electrochemical properties, making it a better cathode and a better battery. So now that leads us to present day, where lithium cobalt oxide has now been the most commercialized cathode material for decades. So now we go over how this product has impacted our lives. So overall, the Department of Energy has claimed that lithium-ion batteries power the lives of millions of people every day. So on a very basic and high-level standpoint, this is something that impacts millions of us every single day, and a lot more every single year, obviously. But another key impact is electric vehicles. Lithium-ion batteries are at the center of EV production, and EV adoption has shown a decrease in NO2 pollution by 0.41 parts per billion and 3.2% increase in annual age-adjusted rate of asthma-related emergency department visits. So not only is it improving the environment, but it's also helping out with health risk incidences. And then lastly, just on a more general level, EV sales have exceeded over 10 million in 2022, showing that this is a widely used thing that's helping people get from point A to point B as well in their vehicles. So now we're going to be going over the origin and processing of those key materials.
So sustainability and environmental impact of lithium ion batteries. So what happens to lithium ion batteries at the end of their lives? Batteries of all sizes can be recycled or refurbished at the end of their lives. Anything from battery in an EV car to a battery in your TV remote. The main challenge is that they are deemed hazardous and can leak battery acid, so they must be taken to a special recycling and disposal center. So how are they recycled? The first step is shredding the battery into multiple different substances, but the main material of interest is called black mass, which contains lithium, cobalt, manganese, and nickel, as well as other metals that may have been in the battery. Then it goes through further processing like smelting and leaching in order to get the metals out in order to reuse them. These metals are expensive due to the cost involved in the extraction process, which also has great environmental impact, which I will touch on later, making this a really beneficial process. Over here to the right is an example of what black mass looks like. So the recycling process is so valuable that many car companies want to create a closed loop ecosystem for their EVs, meaning that at the end of the car's life, comes back to them, they recycle multiple parts from the car, including the batteries, and can reuse the substances that are reusable. Volvo, Toyota, and BMW are all companies that have plans to do this. The other route companies can go is to refurbish the battery, which means they refresh the battery packs as long as they're defect-free, don't have any punctures or flaws and things like that, and replace some of the cells so the battery can be reused again. Nissan does that with their Leaf in order to provide consumers an alternative to a brand new battery when theirs breaks down, so they can get a new one or a newer one at a lower cost. So the extraction process of lithium, whether it's through salt brines or mine, is extremely labor intensive and harmful to the environment. Fossil fuels are used in the process, and this, along with the physical manner which it's done, can cause soil degradation, high water usage, which can affect the surrounding population and impact biodiversity. Additionally, child labor is sometimes used, which has multiple moral and ethical issues. So pollution, waste generation, water consumption, and CO2 emissions are very hard for environmentalists to directly determine, because there's a wide range of the processing of lithium and many different components affect it. Which fossil fuels are used? For example, China uses coal, which has a greater impact with CO2 emissions compared to other ones. Metals are sometimes exposed to drinking water and land, and deforestation can occur in order to be able to mine it, which can indirectly increase CO2 emissions. A water consumption estimate for salt brine specifically is 2 million liters of salt water for 1 metric ton of lithium. CO2 emissions for a 1 kilowatt battery in the middle of the range, which, as it is an estimate, is 150 kilograms. So these all have very high rates, but they are, in general, lower compared to non-EV cars over their lifetime. However, there are alternatives. Lithium ion. Traditionally, lead acid has been an alternative. It has a much lower energy density and shorter life cycle. Nickel cadmium is another alternative. It has a higher energy density than lead acid, but still much lower than lithium ion. And it also uses extremely toxic materials. Nickel metal hydride has a higher energy density than nickel cadmium, but lower than lithium ion and a shorter lifespan. However, it is used in some applications where it's okay to have a shorter life cycle and things like that. For example, cameras. And then sodium ion. Sodium ion is a much more abundant than lithium and very much less expensive due to the ability to extract it. But this is a much newer technology that still needs more research before it really becomes feasible on a large scale. And in general, as you can see, there's also lithium polymer on this chart to the left that has an extremely high energy density. However, it's not really feasible to use because it has a very high risk involved in the operation of the battery that just wasn't worth it. Thank you. I hope you learned a lot about lithium ion batteries.